How is that? Okay, I know Tim will be back. I'll shut the door.
Taking a break.
Not a love to over there. Like there is. One number. I remember stuff better.
Well, if you guys have noticed, we have 2 chapters this week, and we have 2 chapters next week. So it is a lot of content. The reason is because we're getting to this more advanced stuff. Our textbook has just kind of condensed things a little bit. Each of the chapters are short, and they kind of overlap each other a little bit. So we'll be talking about each of them, and you might have to look through all 4 of these chapters to find things, which I know is kind of annoying, but that's just the way they split it up. So chapter 20, we looked a little bit at last time. It's the chapter that talks about lists, stacks, and queues. And then chapter 22, we're going to look a little bit at today. It talks about developing efficient algorithms overall. Chapter 23, which we'll start on next week, talks about sorting. And then chapter 24 talks about implementing lists, stacks, and queues. So there's a lot of overlap. A lot of the same kind of thing going on in each of the chapters. So some of the topics that are in some of these chapters, you guys just might need to remember that that's available, you know, or keep some information in your notes about how to do these things. But today we're going to talk about developing efficient algorithms. Jim was talking a few minutes earlier about an assignment in a class where he needs to do some things. And he realized that he had done an assignment almost like that in another class. So he's able to take that code and apply it. That's because he developed an efficient algorithm, right? And his algorithm that worked in this one programming language is going to work just fine in this other programming language. And that's the way things are. That's why usually as you go through classes here, you'll find one that makes more sense to you. That's not because it was so much better than the other one. It's because your brain had processed enough information at that point to be able to accept the information better and to be able to understand better. So usually people struggle a little bit through their first programming class or the first one that's challenging to them, and then they do a lot better through the second one. They do even better if they could do that first one over again, because then they'd really have those concepts. But that's just kind of normal. Because every time we look at these algorithms to do some sort of process, it triggers new things in our brain, because the first time we look at it, we're just trying to figure out what it's even talking about. Then the second time we've got that basic concept down, we're going, oh yeah, I could apply a little bit of this information. So in this chapter, you'll see if you get on Canvas and look, there are some videos posted. And that's the idea with this chapter in the videos, is that to do the assignments for this chapter, those videos will step you through things, and then you can pause them if you want, or fast forward through things that you don't need any help with, so that you can get everything done. Because we are talking about complex algorithms, not easy algorithms, because that's our point here for this section, is complex. So how do we decide whether an algorithm is complex or simple? Sometimes when I've said, oh, this is a really easy thing to do, you guys may not have agreed with me. Other times I thought something was tough and you thought it was pretty easy. Is there any sort of formula we can use to actually say this is complicated? Yes, there is. The formula that we can use is called Big O. So Big O notation is a whole theory about performance and complexity of algorithms. So whenever we're thinking about creating a new algorithm, a new program, we're going to be thinking about how this is going to operate. How complex is it going to be? Do we need to take some sort of steps to improve performance? Is it going to be so complex that it'll run for 12 days and we'll never get results back? Is that acceptable? What do we need to do? So we have to balance those things. Now, Big O notation is a measurement of the worst case scenario of your program. your algorithm. If your program was running in a situation where there were 1 million rows in the database table that it was going to process, how long would it take to run? That's what we're kind of trying to figure out here. Could we do something to make it better? So whenever we're working with Big O, we're starting to get involved with data. You guys are seeing that as we move out of the simple beginning programming assignments to things that are more real world. In the real world, all of our applications are concerned with data, right? We don't write programs to have people type some stuff at the console, display some information, and have it go away, right? That's just not our real world situation. Our situation is keeping track of data, updating data, making sure that data is accurate. So it's all about the data. So when we're talking about data structures and complex algorithms, we're learning how to deal with these different data structures. How does this data work? How can I handle it best? So from a science standpoint, a lot of this stuff is things that you would get the last couple years of your 4-year degree. So we're looking at kind of an intro to these advanced topics. Another way that you could get some of this experience is if you did some actual software projects that had a lot of data. So here at OTC, you'll see when you take the SQL class and the capstone class, that's how they're set up to try to give you those experiences without you having to go get that 4-year degree, so that you have some experience working with those big quantities of data before you go out and get that job. And that's why people like to hire you guys, because that's a big deal. And a lot of the universities, you don't get that opportunity. Now, you need to be able to understand some basic functional patterns of data before you can be effective. So we don't want to think too hard. We're not talking about reinventing the wheel. We're talking about using the wheel. How do we use it? How do we take advantage of it? So when we're thinking about data, we're going to need to be thinking about storing data, searching for things, sorting things, doing all of those common data type things that we have to do. So each of those things have patterns that have been developed over the years. You might come up with a new pattern that works better than any of the existing patterns. But we have existing patterns for storing data, searching through data, sorting data, and just in general, those data structures like our queue structure and our stack structure. We saw that some of those data structures are suited for different purposes. Some are for real specific purposes. Apparently, if you go to O'Reilly's and they ask you the question about Java and say, how would you switch your name or switch the orders of all of the letters in your name without using a sort or without using a loop structure, you could say, I would put all of the letters into a stack and then pop them out of the stack, and then they would be in reverse order. So think about those data structures, how you might use them. All of them all together are just more tools for your toolbox, because we want you guys to have this big giant toolbox when you leave so that you kind of look like a welder, only it's virtual. We can't see it as much as we can the welder's toolbox, but at least we don't have to get set afire. All right, so what is the most performance efficient thing we can do? Whenever we're talking about Big O, we have some different degrees of complexity. The first one is a constant runtime. When we're talking about Big O, in Big O theory, a constant runtime is referred to as O to 1. A constant runtime means every time my algorithm runs, it's going to do one single comparison. Like I might say, is A greater than B? That's it, that one comparison. Now, if I have an algorithm that does one comparison, is it going to have a constant runtime? It's going to take about the same amount of time to run every single time it runs? Probably. There's no deviation there, right? It's going to do one comparison and be done. So constant runtime. Runtime's not going to change. We're doing one comparison. Now, when we're looking at this program, we're not talking about how many data items are going to be involved. That's irrelevant because we're just talking about one comparison. So O to 1 or O with the 1 in parentheses. constant runtime. Now, next, we have the linear runtime. So an algorithm that has a linear runtime is one that compares the first element to every other element in an array. Now, when we're doing a linear runtime type algorithm, we're going to be doing n-1 comparisons, where n is the size of our array. So over here, if I'm going to search through these people for Abe, I'm going to search through 14 people, right? The first one I'm already going to be checking. That's why they do n-1. So I'm going to be searching that degree of individuals. But if I'm searching this whole group of 100 people for Abe, think how much longer it's going to take. Now, if I could stand there and just yell, that would be great, but I can't. I'm a software program. I'm going to have to ask every single one, right? That's how I do my comparisons. I have to ask each person, are you Abe? Are you Abe? Are you Abe? So that's going to take me a lot longer to do with this group of 100 people than it is with this group of 15 people. So a linear runtime is dependent on the size of the group. The resources required are in direct proportion to the size. Now, some important things about Big O terminology here. As n grows larger, our number of things, it is said to dominate. It becomes dominant in our expected runtime because the more things we have, the longer it's going to take to run. So the Big O theory highlights these dominant terms. We're noticing now that our data can have an impact on our runtime. Now, when we're looking at a linear runtime with Big O, it's going to be written like this, O to N, with the N in parentheses, and we'll say O on the order of N, or just order N. So why is it linear? Well, we're probably going to take the same amount of time for every comparison we need to do. So if it's going to take me half a second to ask each of those people, as I add more people, my runtime is going to grow in a planned, orderly, expected fashion, a linear fashion, because it's going to just take that much more for each item that I add. So let's look at searching. We looked at these animations last time, so we won't look at them today. That's why I was searching for them, because I knew they were somewhere, but I was in a different presentation. So a linear search, the first one we looked at, remember the array was out of order, and we said, I want to find the number 8, and we searched through. We saw that it was super inefficient, right? Because theoretically, we maybe had to look at every element in that array to find one that matches. So a linear search, it's a linear runtime. It's going to be impacted by how many elements are in our array. Now, the next type of runtime that we might encounter is the logarithmic runtime, O log n. Now, whenever we're talking about a logarithmic runtime, it's like item A is being compared to all of the items in set B. So if we add more items to set B, we're going to add to our runtime. But if we add new A's, we've created a logarithmic increase, right? Because originally, for this one, I had to search 16. Now when I add this one, I have to search 16 more. When I add another one, I have to search 16 more. So every time I add an element to A, I'm creating a huge or logarithmic increase in the size of the set that needs to be processed. From Khan Academy, they say every doubling of the occurrence of n, our number, causes a logarithmic increase in resource requirements. So think about processing employees. Say I've got an algorithm where I'm going to read in our 500 employee records from the database. For each of those employee records then, I'm going to have to do some work. I'm going to check their tax exemption status. I'm going to check to see how many dependents they have. I'm going to check to see if some things about their address. Do they live in the same town that our company headquarters are? I'm going to check, 15 or 20 things about every employee. That's going to take a certain amount of time. As I add more employees, I'm going to be exponentially increasing the amount of time it takes, because now I have to do all of these activities for every single employee. The best way to think about it too in that respect would be, for every employee, I'm going to check every other employee in the list to see if they're related. Then as my list grew, I would continuously be adding logarithmic properties. This one is one of those ones that's kind of hard to visualize, but when it's happening, we know it. So the binary search we looked at last time also. The binary search is an example of increasing efficiency, because we said the linear search is so inefficient, it can take freaking forever. How can we do something that can run faster? And developers worked on it, and they said, we could do a binary search by sorting that data in the right order, and then we could greatly reduce the performance requirements of that search. So a binary search is an example of a more effective algorithm. Now, another type of big O is the quadratic runtime. And this is where, like with that employee thing, an algorithm compares every element to every other element. So here we have two arrays. I'm going to take item 1 in this array and compare it to every other item in array 2. I'm going to look at item 2 in this array and compare it to every other item in item 2. And as I go, I'm going to be constantly doubling my runtime. Now, when we're working with a quadratic, every doubling of the occurrence of n causes a quadratic increase, an n squared increase in resource requirements. Now, when we're referring to this one, we call it O on the order of n squared, or order n squared. Now, in the chapter, there are some other things that we need to be aware of that are just common algorithms. These aren't things that you're going to have to do specific assignments about, but they're pieces of information that are in the textbook that could be really valuable to you for if you have a need. So let's look at the towers of Hanoi. I say be sure to check video because I want you guys to watch it. Let's make sure I don't have some weird video here too. There it is. I think I've got sound. So the Towers of Hanoi, you might remember it as a kid's game, right? And in the game, we have these round things stacked on the poles, and we have to rearrange so that instead of the biggest to the smallest, we're ordered smallest to biggest, or we might be that they're out of order and we're trying to get them ordered biggest to smallest. Whatever the situation is, we've got to use the 3 poles to reorder all of the items on there. So just this awesome video, put you to sleep. Think about how you would have to do that. And if you have kids and you've played with the block sorting things a lot, you've seen it quite a bit, you know how to do it. Think about how you would write an algorithm for that. What would you do? You would have to take the first one off of this tower and put it on this tower. Take the next one, do something with it. So he did it really quickly. In the textbook, they give you a nice algorithm and formula so that you can try messing with it, doing some Towers of Hanoi assistance. Now another one is the Sieve of Eratosthenes. Probably not saying that correct. I'm going to try it. This is an algorithm for locating a prime number.
I'm now going to introduce an ancient method for generating a list of primes up to some limit n, called the Sieve of Eratosthenes. Now, Eratosthenes was born in 276 BC. So this method, is over 2,200 years old, but it's very simple and elegant, and you can teach it to any child. Now, let's say, for example, we want to calculate all the primes up to 100. This would work in the same way if we calculate 1,000 or a billion. Proceeds as follows. Assume all numbers are unmarked. Gray is unmarked. We start at the beginning. And if we find a number that is unmarked, we know it's prime. So we hit 2, and we say 2 is prime because it's unmarked. And then the second phase is, now we can eliminate all multiples of 2 because we know they're composite. So bam, we jump along and we eliminate all multiples of 2. Red means composite. And now we repeat. We step along from 2 to 3. 3 is unmarked, so we mark 3 as prime. And now we can eliminate all multiples of 3. And a really simple optimization is, notice 6 is already crossed off. We actually cross off the multiples starting at the square of that number. So 3 times 3 is 9. We start at 9 and mark all multiples of 3 as composite. And again, we go back.
Now, as he's talking and doing this, be thinking about how you would code that. How would you code that? Because he's giving you like a really efficient way of handling it. Are you going to have one array? Would you have more than one array? What would you do?
We jump along to 4. Well, 4 is marked, it's composite. We jump along to 5. We found an unmarked number. 5 is prime. Now, 5 times 5 is 25. We go to 25. We mark out 25, 30, 35, 40, 45, and so on. Those are composites. We proceed forward until we hit 7. We know 7 is prime because it's unmarked. 7 times 7 is 49. We mark 49 and all multiples of 7 above it as composite. And now we move along until we hit 11. 11 is prime. And notice now, 11 times 11 is greater than 100. So we can actually stop at this point. We could have stopped at 10 even. Because now all remaining unmarked numbers, if you'll notice, are prime. And we could, in one swoop, mark them all as prime. And that's the whole algorithm. It's so simple. And just to generalize how we do this, so we could write up a program to perform this, is if we want to find all primes up to some number n, we first create a main loop. So we have for all numbers a from 2 to the square root of n. So notice here, we stop. When we hit 10, or I showed it as 11, we actually stop because we have found all primes. So from 2 to the square root of n, we proceed as follows. If a is unmarked, then we know a is prime. And when we find a prime number, we mark all multiples of a off as composite. And that's it. So you find a number prime, mark off the multiples, go back to the beginning, increment a by 1. So we're on 2, then we go to 3, then we go to 4, 5, and so on. And when we're done, we have all primes. Notice here that this is also a loop. So we have a main loop for when we find a prime, this marking off of multiples is also a loop. So it's important to notice here that we have a nested loop. We have a loop inside a loop. Here is an example of this algorithm in action. I wrote in JavaScript below. If I put in 100, here are all the primes under 100. If I put in 200, here are all the primes under 200. And if I put in 850, here are all the primes under 850. And below, I have this program with a recording explaining how I set it up.
Yay. So now your assignment has to do with prime numbers, but you're not going to use the Sieve of Eratosthenes because our number is too high. That probably wouldn't be an effective algorithm for us with what you're looking for. But it is an option. So we'll have a different algorithm that we'll use. I wanted to bring up something in our textbook before I went on from there. When we're looking at prime numbers, you may not be aware, but there's a $150,000 award out there that just is waiting for people that discover a new prime number that has more than, what is that, 100 million digits? So the last new prime number that was discovered a few years ago was actually discovered at CMSU in Warrensburg here in Missouri. And they have a computing site, probably some old computer sitting in a closet somewhere. I know it's in Warrensburg. But anyways, they have this computing site that just chugs away and is working towards finding another prime number that just runs and runs and runs and runs and runs. In Eureka, a couple of years ago, they hit one. And so I guess they got whatever award it was. They were on the news and things like that. It was very exciting. So I don't know if it always stays 150,000. Let's check that site. This is in our textbook that they talk about it. And looks like we would have to do some searching to see if that reward is still out there, or if UCM took it. When they got it, they might have taken it, but I don't think so, because we are looking at a pretty new version of our textbook, unless they just didn't update. So we do care about prime numbers. We all care about prime numbers. And actually, a couple years ago, a student that left here sent some information back about a new algorithm for calculating prime numbers that he had come up with that might be great for him. We'll see. So the sieve is great. Sieve, feels like a filter, like a strainer. So we're taking this Sieve of Eratosthenes and straining all those numbers to come up with only our primes. So that's why it's named that way. Click. Must not be on the right place. Okay, now another algorithm that is presented in chapter 22 is divide and conquer. And this one is, again, super important depending on what you want to do. With divide and conquer, we have a bunch of points like X, Y coordinates that we have somewhere. And we're trying to figure out what is the closest pair of points. You would do this if you were doing some sort of mapping, right? If you were in the trucking industry, this would be extremely important to you, because when you're sending your trucks into cities, sure, you could use Google Maps to figure out how to get to the city, but once you're in the city, you might have specific algorithms that, with data that you wanted to apply to make sure the truck was moving around town in the right order. Let's look at this video. We want to find the closest pair of points of all of the points that we have. I know it's not holidays, so think of them as Easter
It
eggs.
was 10 to midnight on December 24th, and all was not well in the far, far north. Some little elves were wrapping 1,024 toys, roller skates for 1,024 good girls and boys. At 10 to midnight, the elves called St. Nick. Tonight, all the boxes had been filled extra quick. St. Nick was thrilled. Right then, fill up the sleigh, 1,024 boxes, and we're on our way. Then Mrs. Christmas burst through the doors. Where are your dirty socks, Santa Claus? The young elf cried, Santa, I'll drop your dirty sockses in one of the 1,024 boxes. Quick, unwrap every single box. I'm not leaving till you find those socks. Sorry, Santa, said the supervisor elf. Us workers are all union, and we finish at 12. Said Santa, no need to be unpleasant. I've got a big pair of scales. Just weigh each present. They'll all weigh the same when you put them in each bucket, except for one, and that one's the culprit. With all due respect, replied the supervisor elf, it'll take a jolly long time, and you can do it yourself. If we could make one comparison every second, we'd be here till 12:07. A little elf piped up. I've got an idea. We just need to use divide and conquer here. Put half the boxes on that scale and half the boxes on this. Whichever side goes up, that pile we dismiss. The supervisor elf, with an unimpressed gaze, pointed out, we'll still be here for days. You've narrowed it down to 512. Hardly any help from this little elf. Wait, said the other, only beginning his campaign. Watch what happens when we halve it again. So they halved it again, and now their fix was narrowed to 256. Then, after their third comparison of weight, their problem was reduced to 128, then 64, then 32, 16, 8, 4, 2, it's true! On the 10th comparison, with much joy, this elf had found the erroneous toy. A job that could have gone well beyond the time limits took just a matter of minutes. So the gift was replaced, the elves went home, and Santa was set for his worldwide roam. No poor child, far or near, will have to smell Santa's dirty underwear. But first, the little elf was approached by St. Nick. Where did you learn your clever trick? The little elf replied, on magic, I make no reliance. All I need to use is a little computer science.
Oh, cute. I like the dirty socks. And if you notice with that algorithm, how would that apply to these point distances? Well, again, I'm going to say, what is the distance between all of the points in this shape? And I could add those up and have a total of all of the distances between points. And I could do the same thing for all of these shapes and then compare them and find the one that has the smallest. And again, I could keep doing some sort of divide and conquer scenario like that until I figured out which set of points were the closest. So not exactly as easy as the socks. But notice with the socks, we're trying to reduce the number of comparisons. We went from 1,024 comparisons of every single box to, what did they say in the end, 8 or something, I think was 10. 10 was their final number. So we were able to really, really improve performance there.
Yeah, but how much time did it take for them to stack and unstack those boxes?
Yeah, that's true. Just a few seconds. And sometimes it doesn't matter, because if it's something that we wouldn't possibly be able to, you know, unwrap and rewrap and all those kinds of things, it's still going to be faster. Okay, 8 queens. Now this one, I want our math people to really focus on and help us all with. This is an algorithm, and you can see I don't even have anything written down. Let's just watch it.
Honey is a free browser add-on available on Google, Opera, Firefox, Safari. If it's a browser, it has Honey. All you have to do is...
There we go. Got it.
One of the famous puzzles that you can play with a chess board. It's not chess itself, but it's a puzzle you can play. The standard 8x8 chess board and queens. So a queen, if you don't know, a queen is the strongest. It's the best piece on a chessboard because it can move any number of squares to the left and the right. It can move any number of squares up and down, and it can move diagonally as well. Any number of squares. And oh, if there's another piece in its way, it takes it. Ah, gotcha. Right, so that's how a queen moves. Diagonally, up and down, left and right. Now the puzzle is, can you place 8 queens on a chessboard so that none of the queens can attack each other? So all the queens are safe. So this wouldn't work as a placement because we've got 1 queen here. I can take another, they're under attack, but maybe something like this would work just fine. Now I've only got 2 queens here. All queens can take each other queen, so the colours don't matter. The question is, can we place 8 queens on the board? Can we? Okay, well, how many ways can we place 8 queens on the board. First of all, how many ways are there to do that? Let's look at that first, right? Which does mean that we've got 56 blanks. I think we can do this calculation. I think even Brady can do this calculation. How many ways can you arrange 64 objects, Brady?
64 factorial.
Yeah, 64 factorial. If you have 64 objects, there are 64 factorial ways to do that, which is 64 times 63 times 62 times 61, all the way down to 1. So there are 64 objects, 8 queens and 56 blanks, but you can rearrange the blanks between themselves and it doesn't change the position on the board. So we're going to divide by how many blanks there are, 56 factorial ways to arrange the blanks. So we have to consider that the queens are the same. So I can move the queens between each other, I can commute the queens between each other, and it doesn't affect the solution, the positions they are on the board. So for that reason, we are also going to divide through by 8 factorial. There are 8 queens, and they can be swapped around between each other. So we'll divide through by 8 factorial. So the number of ways you can arrange those 8 queens naively is 4,426,165,368. So there are over 4 billion ways you can place your 8 queens on the board, and that's naively doing it. That's not considering how the queens attack each other. So you're going to get silly solutions like this one, or this, or this. These are no good. These aren't solutions. So how many solutions are there out of that 4 billion figure that do work so the queens don't attack? What do you think? It is, in fact, only a small fraction of this 4 billion. There are 92 distinct solutions. That 92 out of 4 billion as a percentage is tiny, unbelievably tiny. So here is one of the solutions. You could place a queen here, and put one here. They don't attack each other. They're not in the same row, they're not in the same column, they're not in the same diagonal. And put a queen here, again, not in the same row, column, or diagonal. I could put one, I think, down here, one here, and maybe I'll put one here, and here, and where did I put it? Here? Yeah. I think I got away with that. So that would work. No queens are attacking each other. Now, there are 92 distinct solutions that you can have. But that includes rotating the board and reflecting the board as well. So they're not all going to be really different. Some of them are just turning this 90 degrees. That would count as a solution. Now, there are 8 ways that you could rotate the board and reflect it. 4 rotations and 4 reflections. So how many actual individual ways are there to do it? There's 12. There's only 12 fundamentally different solutions. 11 of them have 8 reflections and rotations, pages up to 88. One of them only has 4 rotations and reflections. Actually, this one I drew. This only has 4 different solutions, because if I rotate it 180, it's symmetric. So that only has 4, that has half as many. But the others have 8. So that's 92 distinct solutions, 12 fundamentally different ones. So you can do this, yeah, you can do this with other pieces. Can you place 8 knights on the board without attacking each other? I think that would be quite easy. Could you place 8 bishops on the board without attacking each other? I think that's quite an easy problem as well. Maybe 8 rooks. So again, I think these are easier problems. Although how many ways you can do it, that's a much more interesting question. How many different ways can you do it? We'd like to thank lynda.com.
Okay, so we went all over to Khan Academy and lynda.com and all the other places. Now, in the textbook, the 8 queens example that they give you is solving the 8 queens problem using backtracking. So again, it's an interesting algorithm. but it is pretty complicated if you notice. Okay, so Big O, that's Big O in a nutshell. Big O is how complicated is it, and can I make it simpler? There's an entire Code Academy course. Let me see if this link still works to Code Academy because I have not double checked it. The actual Big O information that's contained within Code Academy was part of their computer science path, but I think it went into the pro group when they started charging for things. So I don't think it's something that we can go through anymore. If you look at this other link, this PowerPoint should be on Canvas for you, by the way. If you look at Rob Bell's link here, there will be more of a guide to Big O. So in our textbook, they do ask you to identify specific algorithms as to the Big O classification of the algorithm. You know, is it O sub n or O log n? So there will be questions in the quiz bank about that. Now I wanted to bring up the assignment. In chapter 22, our programming exercises from the book. And this week we have exercise 22.8 and 22.14, and they are related. So that's why there's both of them. So if we look at our textbook, and I'm going to go find those, 22.8 is very interesting. You're going to be looking at trying to determine all of the prime numbers up to, what is that, 10 billion? Write a program that finds all prime numbers up to that number. Don't use that number for your testing. Use a very much smaller number for your testing, because if you use this number for your testing, it will be running for quite some time and you won't be getting any testing done. So make sure.
To use the Unix.
Yeah, you don't have a Unix machine, do you?
I
I don't have one for you, so yeah, we got to change some things a little bit on this thing because they're wanting us to have our own server.
Yeah,
Do
I was
it.
really wondering.
Yeah, what are we going to do? Because we don't have those things. So we're going to have to make it a smaller number for sure. And also, I would like to test your programs. So I probably don't want that huge giant number either. But if you're going after the 150,000, you know, you're going to have to go to a much higher number, but you probably need a better algorithm.
So if we use that number, probably won't get a grade until next spring.
I don't know. Don't know what'll happen. Now, what's interesting about this one, a few other things, let's look at it. As you're going through processing numbers, when you find a prime number, you're going to write it to a binary data file. We're going to look at that chapter real fast to kind of review how do we write to a binary data file. Now, when you find a new number, you'll see they want you to kind of have this moving array. So they want you to have an array that loads all of the prime numbers from our file into an array so we can skip past all of those and know we already know they're prime. So basically this file is like a restart point for your program. So say your program's been running for 12 hours, it's found 20,000 prime numbers and it's written them all out to that data file, that text file. You have to cancel your program. You've got to go to school. You've got to take your computer somewhere. When you come back the next time then and start your program up, the first thing it should do is read through this data file and say, oh, I've already identified all of these numbers as prime, so I'm going to put them into an array so that we don't process them again and try to do that. So that's the first thing it'll do when it starts up. Does this data file exist? Read it in if it does. Once you've gotten past the prime numbers you had already identified as prime, so in our very first run, at the beginning of our numbers, you'll start using their calculation to figure out if a number is prime. Now, we don't have a Unix machine. We're not going to set up a batch job to run on the Unix machine. But we are going to simulate that by saying if we stop running our program, we should be able to start it again and pick up from that data file where we left off. So we don't have to have any big numbers. We just have to have that data file. Okay, and then the other assignment, 22.11. That's not right. Has something changed? Might have to fix this for us. 14, I just have to get in the right place. There it is. I just couldn't get down there. 22.14 is our second one. Now, in 22.14, we could actually do this one together, but you'll have more fun if you do it on your own, right? Like a lot of our other programs in our book, they want you to use these listings. Do you have to write these? No, you're just going to click on that link and go find that listing. So one of these is going to be finding prime numbers using the algorithm they give us in the book. One of these is going to be finding prime numbers using that Sieve of Eratosthenes. And one of them is using prime numbers in some other way. So what your job is to do is to take those three listings and set them up to run repeatedly. And you want to figure out how long does it take. So if I ran it with 8 million records, this one took, 2.5 seconds. This one took 3.5 seconds, 4.5. So what we really want here is just a loop to keep running these three things over and over and over with different size sets so that we can get some statistics for how long they take to run. Now, because these are kind of complicated, without a doubt, there are several videos out there for you on Canvas. Like I said, they're going to walk you through different parts of it, and there are some that you're going to want to skip, some that you're going to want to do. First of all, let's go look at writing a binary data file. This is in a chapter that isn't really covered well in Java 1. I think that it is, where? That would be it. Thank you. I was thinking 10. For some reason, I had chapter 10 stuck in my head. So chapter 17. Now, it is a really short chapter. And that's part of, I think, why it's not specifically in one of our classes. But it's still something that's kind of new for us. So in those videos, they definitely show you how to write this file and how to read this file that you're going to need. So you have a lot of different choices here in approaching these two assignments. Look at everything that you have to do. This is a big one. Remember last week I said the sort and shuffle hopefully are easy because these ones aren't. All right. But with all of the videos and everything, they should be fairly simple for you. Now, make a decision. First of all, do you want to start with that second assignment that just has you use the existing listings and compare performance? That might be easiest, it might be hardest. It kind of depends on your point of view. Do you like pulling in that code from other places and just getting it to run, or is that hard for you? So you might want to start with that one. Then for the prime number assignment, you have some choices. You could do the prime number stuff and don't worry about the data file right off the bat at the beginning, or you could focus on the data file and then add the prime number calculation in So lots and lots of different choices. You have enough of an assignment here to actually wrap your arms around it, get your teeth into it. It's not just a little simple thing. So decide how you want to do it. Now, the other thing that you have here are your classmates. So if you guys stick around and work together through some of these things, you might be able to figure a lot of it out. If you'd rather go home and start watching videos and getting it done, that's fine too, because there's definitely those different choices. Let's look at Canvas, how many there are. So the videos, I haven't looked at recently, but I've heard from some people that are in the online class, of course, and we have some people in the online class that have both assignments done from watching the videos and stuff. So I don't think you'll have any trouble going through them. But there are 3 of them. So 2214, if you notice, I kind of put first, the one where we're comparing the different performance options, because to me, that gave me an opportunity to look at those different algorithms of how to calculate the prime numbers before I started getting into the data file and all of the other pieces. Okay, questions about them? Know what you need to do? We're taking lab time from now so that you can have an opportunity to get started on these. And like I said, I think if you talk it out with some of the other people in the class after you've had a chance to look at it, that will probably help you more than anything. But you've got this.